still have lab, y'all was exam was there last week?
Next
We had
episode, ours.
we had a quiz last week, the exam is next week.
One got any questions when we started?
Yes. One question. On the theorem about. Get it on my laptop. The theorem where it defines linear independence of elements in the group. Are the two things, one, are the m's assumed to be elements of a specific set? Are they assumed to be integers? Okay. And then it uses the addition sign. Is that just generally like, that's any abelian operation? 'Cause
Well,
it's
you
a
can
group.
certainly write a Abelian multiplicatively, if you assume the multiplication means, but it's very common, and we will, when we do the fundamental theorem of finite generated group, we'll write it. So if you see addition, it's usually assumed that it's Abelian,
Yeah.
right? The converse isn't always true, right? So. Okay, so any questions? So I've written up, the last thing that we did is, we didn't do like, part 4 of part 1. That's in the notes, and it's pretty self-explanatory, but let me know if you have any trouble with it. I'm gonna move on to the following theorem, and this is the important thing. So what does a free abelian group look like? Well, our theorem says it's just a direct sum of some number of copies of C. Could be finite, can be infinite at different cardinalities. And size determines everything in the following sense. Any two bases bases. No. And we can take it a step further than that. Any two free abelian groups are isomorphic. If and only if their bases have the same cardinality. So in other words, if you have any free abelian group and you pick out two bases of it, they have to have the same size. And you can take that a step further by saying, if you have two free abelian groups, just look at their bases, which is a well-defined term. If they're the same size, the two are isomorphic if and only, right? So let me take you through a sketch of this. The first thing that we're going to do is consider the case where suppose X and Y are bases. Okay, so I'm gonna take steps on this. I'm gonna sort of demonstrate why this is true. We're all bases, or if you compare two bases that are both finite, then those finite sizes have to be the same. From this, it will follow that if it has a finite base, it can't have an infinite base. And then from there, I'm gonna kind of sketch over the last bit about where you have infinite bases. But let's suppose this. Okay, so suppose we count two bases, x and y of A, one size n, one size n. So A isomorphic to so A is isomorphic to n copies of Z, and it's also isomorphic to m copies of Z. So what is the problem with this? I mean, this doesn't look right, does it? Right? How can it be isomorphic to both n and m copies? Well, let me do some counts. Consider so it's easy to check that A mod 2A is isomorphic to this is a contradiction. This is a contradiction because this would give the order of A mod 2A is equal to the n power, and this gives the order of A mod 2A is equal to the n power. Well, actually, let me not structure it that way. I didn't assume that n and n is different. That's the so n. So the conclusion is if you have two bases of the same size, pass the subgroup, A mod 2A is isomorphic to n copies of Z2 and m copies of Z2. Because of the fact it says 2 to the n elements, it says 2 to the m, I must exclude the n equals m. Basis. X. Yeah, all. Because really what that means is, if for example, Y was an infinite basis that had infinitely many elements, then you have a direct sum of infinite copies of Z2. And now you've got 2 to the n power equal is infinite. That's impossible. So the only thing really left is what happens what happens in the case of an infinite basis. So So in this case, the cardinality of the three abelian group is the same size as the cardinality of the basis, right? This distinguishes from finite cases, right? But for example, if A has an infinite basis, then every basis should be infinite. And the smallest that X can be is countable. And since Z is countable, when you have countable unique copies of Z, it's countable. And this is kind of a set theory thing, which is why I'm not going into details here. But it turns out that if you have for any cardinal number A, if X is an infinite cardinal, then countable number some countable unique copies of Z has the same cardinality. And that gives you the rest of the statement here. Now, there's also the claim that any two, yes.
So for the last statement that we made, are we assuming that X is countably infinite?
At least countably infinite.
Okay.
At least countably, right? That statement is certainly not true if that's finite, or if it's finite. We need to know that two free abelian groups are isomorphic if and only if their bases have the same cardinality. Well, if X1 equals X2, then there exists a bijection F from X1. Right, of course, that's what it means for two sets that have the same size. And of course, there's an inverse bijection. Just take G to be the inverse of that. Right. By the universal mapping property, F and G induce homomorphism. F bar from X1 F1 to F2 and G bar from F2 to F1. And since G see that when you compose F1 G bar from F1 itself and F bar from F2 to itself,
So what are you saying the F bar exactly is in this case? Like, what does that do?
right? So it's just the induced homomorphism. So, for example, if let's say that F has this rule here, F of Xi equals, well, so F is our bijection, right? Then basically F takes each Xi to Yi. Oops. And the domain is all the elements x to the basis here, the range is all the y's to the basis of x2. And so this induces a homomorphism from F1 to F2. And how does it work? Well, take your typical element here, free group, right? What it is it's a linear combination of bases, right? And let me write this out dramatically. Right, this is a linear combination of bases X. Now, before you panic too much, remember this is a direct sum, and so all but finitely many of these i's are zero. You okay with that? And the output of that should be the sum of n I f, which is sum. So that's what homomorphism works. Input linear combination first basis, output linear combination. Okay, next theorem. And you might have smelled this one coming because this looks very similar to what we do with free groups, and I'll kind of maybe wave my hands at it because we did something very similar to this theorem. So 6, 3, 3. Yes, the homomorphic image. Increase. So, and free Abelian group. And we chose. The range. Okay, so if I walk up to you on the street and give you any Abelian group, it's the homomorphic image of some free Abelian group. And if the group that I want you to be the homomorphic image to is generated by some set X, then the free Abelian group can be taken to be of rank, and by rank I mean the cardinality of the basis of the free Abelian group, the same thing as the size of the generating set. So in particular, if you have a finitely generated Abelian group, it can be realized as a homomorphic image of a finitely generated free Abelian group. So if I have a free Abelian group with 10 generators, then I can realize that as a homomorphic image of 10 copies of zero. Okay, that's what that means. And yes.
Every group is the homomorphic image of an Abelian.
You know that every group is the homomorphic image of a free group.
Oh yeah, of free groups.
So
Oh,
it is true
that's
that-
different.
that's right. That's right.
That's
Any Abelian group is also the homomorphic image of a free group, but it's more tangled. This says a little bit more. It says that an Abelian group can be written not only as a homomorphic image of some complicated free group, but you can actually do it as a homomorphic image of a free Abelian. Right? So that's the difference. Okay. So So let me just sketch this real quick. Suppose A generated by X. And it's kind of a good way to use X I, I. Let it be free. So again, this is the same structure for four. In X, we just forget about relations in A. Then there exists a homomorphism at bar from F given by F bar sum of NIXI. And here the Xi's have no relations other than they commute with each other. That's which in this case because I'm gonna let the function take each basis element to the element in A generator. These Xi's may have relations now. And it's fairly easy to see this is onto because an arbitrary element of A by definition is generated by the set Xi. So there you go. Okay, any questions on this? By the way, I'm going to throw in this lemma now because I am going to introduce a theorem after this lemma that is going to be very important when we do the classification of finitely generated Abelian groups. It's also very important for modules, and it's kind of a neat computational thing. But I'm going to need something first. I don't know what does this remind you all of? I'm on 3, 6, 7. If X1, X2, is a basis for a free Abelian group. And N is in Z. Then for all I not J, the set of elements X1 J minus 1 Xj plus N XAI Xj plus 1 X. This is a very poor choice here. Let's say K and Z. What does that remind you of? It can remind me of something, especially since I'm also teaching linear algebra. Y'all remember this theorem from linear algebra that if you have a basis of a vector space, you can replace one of the basis elements. That's what we did here. We replace xj with xj plus a multiple, right? It also kind of reminds me of that those row operations that you do for matrices, right? So what this says is you can mess with xj by replacing it with a multiple of another basis element, you still get a basis. let's prove this. Okay, we gotta show two things. We gotta show this linearly independent, we gotta show that it spans the original, F, right? So, we call A1 X1 plus A2 X2 plus AJ minus 1, XJ minus 1 plus AJ XJ plus K XI plus 1 0. Suppose that's true. Well, this means, let's see, we kind of arrange this. This means that A1 X plus A2 X squared. And let's see, this is going to show up as AI plus AJK XI, right? Plus AJXJ plus ANXN 0. Right, and hopefully you all will forgive me, because I'm sort of, it looks like I'm sort of assuming that I is less than J, but it really doesn't matter what I put it there. So now when I've written it this way, since the Xi's are linearly independent, this means that every coefficient is 0, correct? So what I get from this, because Xi and Xn is linearly independent, this gives me all the coefficients are 0, so I get A1 0, A2 0. I get the strange deviant here. I get AI plus AJK is 0, but everything else, AJ is 0, AN. Right. And so I've got every coefficient being 0. And what do I have here? Well, since AI plus AJK is 0 and AJ is 0, this implies AI is also 0. Right? And so that means that this new set is linearly independent. Because we started here with these coefficients A1, A2, all the A's, and we've got at this point that all A's are 0 except maybe AI, but this gives me that AI is also 0. Okay with that? The last bit is we need to be able to write everything in terms of its basis. So suppose alpha is an F. Alpha is A1 X1 plus A2 X2 plus AI XI AJ XJ. Y'all see how to write it in terms that you need to? I need to be able to write it as a linear combination of two bases, A1, AJ minus 1, AJ plus let's see how to do it. Right, so what I need is I need to replace this by AJ plus what, KAI? Right, so somehow what I need is I need this guy here, so I'm gonna need AJ. So I've got to get rid of K, AI, X, J. Oh, I don't need that. Yeah. I wrote this wrong, I'm sorry, I need to slur combination X1, go to X J minus 1, X J plus K, better. So I need to replace this with XJ plus XI. Right? And so when I do this, I've got an extra AJK. So what I need to do is subtract this off the XI part. So of course, notice that this thing is exactly equal to this, right? And just subtract this off in the XI part. So this is still a basis. So I can replace any basis element with itself plus a multiple of another basis element, right? That's going to be useful for us. Any questions? Yes.
So just like you mentioned last class about unlike in vector spaces, if you have a linearly independent set which is smaller than the cardinality of the basis, you can't necessarily form a basis which
Yeah, you can't necessarily.
in the same way, if you have a linearly independent set that is the same order as your basis, it's not necessarily the basis.
That is correct, right. So his point is if you know that the basis has cardinality 10, right? So this is a free ability group on 10 elements. Just because you have a linearly independent set of 10 elements does not necessarily make it a basis. Here's a silly example. Just take Z, its basis is 1, right? Or -1, and that's all you got. The linear independent set 5 is not a basis because it doesn't span. And there's no way you can span it to a basis, right? You have to replace it. Okay, other questions? Okay, so here's this kind of neat theorem. This is very useful. It comes up in module 2. Theorem 368. Well, that'd be a free abelian group of finite rank. So this is like a isomorphic to n copies of C, if you will. If A is a non-zero subgroup, then there exists a basis x1 up to xn of F. So I can find some basis of F and an integer R. Some integer between 1 and whatever the rank of F is, and positive integers D1 divides D2 divides R. So what I mean by this notation is D1 divides D2, D2 divides D3, D3 divides all the way up to DR. So they divide as they go up, such that A is free abelian with basis D1, X1, D2, X2, up to DR. Now, let me remark. So what this says is, we kind of draw a picture. So you have F, and it's generated by X1, X2, X3. This is a free abelian group of finite rank. Now, you go sniffing around, and you find some other abelian group A inside, right? Not zero, because zero is silly. Then, actually, let me do the order this way. So you've got some free abelian group, any basis got n elements in it. You find some subgroup. There exists a basis, and the basis you pick to make this theorem work depends perhaps on what A is. I can find some basis where, here, let me break this automatically. XR, where basically these first R vectors, elements of the group, I should say, generate A, but not quite. So you need multiples of these, but see, you can find fancy multiples. You can arrange this so it's the D1 divides D2, which in turn divides D3. Let's do that. Okay, here's a stupid example. The integers, right? I'm not really gonna, this is boring, but this is a starting point. But I bring up the integers because it illustrates why you need these D's in a certain sense, right? Take the integers. What does any subgroup look like that's not zero? It looks just like the integers in a certain sense, right? Because the integers is an infinite cyclic group. Every subgroup is also cyclic, and if it's not zero, it's also infinite, right? So the integers is generated by the basis 1, right? Any subgroup is determined by what generates, right? 5Z, 12Z, 100Z. And so in the case of the integers, it will be X1, and your D would be what it generates, right? And that's basically how you ramp up. If you have 2 copies of C, then any abelian group that you find inside there is either singly generated, in which case you only need one of these, right? And you can rearrange the basis up here to find this. And or the subgroup is generated by 2 elements, in which case you might have to push this around and find the particular X1 and X2, such as this is D1X1 and D2X2. And this goes back into your question again. The reason we have to fiddle around with these D's is because this ain't a field, right? So like for vector spaces, all that D stuff, who cares? Because you could divide out by it if this was a vector space, because all the D's would be units, right? The integers isn't as good as a field, so we've got to have that. But you know what's super sexy about the integers? They're the Euclidean domain, and that's going to come up. We've got the Euclidean algorithm. Not as good as a field, but it helps quite a bit, and it helps us be able to do this trick. So that being kind of the, there's my little teaser, my trailer for the proof. So let's do this thing. Oh, and before I do it, I mean, this is obvious from the statement of proof, but I think it's good to underline it. Number one is, and this is, you'll see actually in your homework that this is kind of a special thing, because one of the problems in your homework is actually to generate a group of two elements that have subgroups that are not finitely generated, right? One of the things you can take away from this is if you have a free abelian group, then any subgroup is also free abelian and is generated by no more than the number of elements to generate the parent group. So a subgroup of a finitely generated free abelian group is also free abelian, and its rank is less than or equal to the rank of its parent. Okay, so let's do this proof. And one is easy. We kind of talked our way through that. The thing is one is the integers. So let's work our way up from there. We'll assume result holds for all free abelian groups. Of rank less than. And so we're going to try to finish an induction by showing that it now works for groups of now we're going to look at ranking. So for this one, we'll let S be the set of integers such there is a basis of F such that there exists a basis of F, which I will call Y1 and Yn. And an element of the form of form. Let's call this S1. Let's say KTY2 of KTYN. So basically, S is a set of integers. These are like the set of coefficients, the basis that you need to squeeze these in here. Now, S is a subset of the integers, and so maybe you kind of see where we're going to go. We're going to do some kind of minimality argument on the positive ones, right? So S is a set of integers such that there's some basis, Y1 up to Yn, and you can write this as an element of A with these integers. Notice that but I write S in that special form because that's the one that I'm going to kind of key on. So notice that by definition, all the K's are also elements of S as well. S is not equal to the empty set as A is assumed to be non-zero. And so there's a smallest positive integer in S. There exists smallest positive. We call it V1 in S. you've got to love subsets of the positive integers, right? Certainly, I would expect 0 to be an S, but among all the positive integers in S, there has to be a smallest one. Since this D1 is an S, there's this some DNA such that D equals D1 Y1 plus, again, I'll call it K2 Y2. And what I'm going to do now is I'm going to use the Euclidean algorithm. I'm going to write each Ki as 2i D1 plus Ri, with each Ri to 0 D1. So basically, I'm going to divide each of these K's that I find here by D1 and find some remainder that's either 0 or smaller in size than D1. Now, rewriting all this, I want to kind of group this thing with the remainders. 1 times Y1 plus let's see, Q2 Y2 Qn Yn plus all these remainders, R2 Y2 Yn. Now, notice that these RIs are in S. Each RIs. Right? Because here we have a linear combination of things being in A. Right? So by definition, all these RIs are in S. By minimality, D1, each RI is 0. And so, what I'm going to do is let 1 equal Y1 plus Q2 Y2 plus Qn Yn, and note that X1, Y2, Y3, Yn was also a basis. And this is by the previous limit, because I've replaced my basis X1, which is Y1 plus multiples of the other basis elements. So inductively, this is still a basis, right? And let me note, D is actually D1, right? Because all these RIs are 0, they're gone, and this is what I'm calling X, X1, that is. Now, H generated by Y2 by 3. Then H is free abelian. And H is free abelian. And F is X1 direct sum. And what we're going to do is I claim, and this will be for next time, we'll finish it next time. I claim that A is the direct sum A intercept. So H is generated by the n minus 1 linear in elements itself is free abelian. F is X1 direct sum H. X is made of the spaces. And this is where we're going for next time to finish things off. Okay, any questions on that? Any questions? Okay, well, I will be up in my office after the next class. If y'all have any questions, scroll by. Other than that, I will see you by Wednesday. See y'all out there.